In this video, I want to look at limits involving infinity. We're going to do a lot more of this too moving forward. In the next video, we're going to look at asymptotes, and so this is absolutely going to be necessary to study asymptotes. But let's just start by figuring out what is happening when x is going to infinity. So if I had the function 1 over x and said, what is f of infinity? Well, we wouldn't do that. Infinity is not a number. We can't go plugging that in. But we can think about what happens as we approach it. What happens as we let our x's get bigger and bigger? If we notice, the numerator in the 1 over x is not changing, only the x's. Let's just start by plugging in some values. So let's start with an x is equal to 1. So we'd have 1 over 1, which of course is equal to 1. Then as x grows to 2, we'd have 1/2 or 0.5. Speeding us up a little bit, we'd have 1 over 3, 1 over 4, all the way up to 1 over 10, which is 0.1. Eventually, we're going to get to 1 over 100, which is 0.01. And I'm sure you guys can see the pattern. This number is getting smaller and smaller. By letting that numerator stay the same, by keeping that the same and letting the denominator run off to infinity, our fraction here is going to 0. Let's look at something that's a little bit more complex. Let's take x squared plus 3x minus 2 over x to the 5th minus 5x plus 3. Just making some things up here. Well, now both the numerator and the denominator are changing. As x changes, obviously x squared plus 3x minus 2, that is going to be changing, in the x to the 5th minus 5x plus 3, that as well. If I think about plugging that infinity in, well, we'd have infinity squared, not really a number. It's going to infinity. The denominator, infinity to the 5th, that is going to infinity as well. But is one of them getting there faster? That's kind of the key here. Not all infinities are equal. Infinity is not a number. Infinity is this idea of going off forever and ever. Not all infinities are equal. So what happens as our numbers grow larger and larger? Well, let me just for a second consider the x to the 2nd, the x to the 5th, kind of ignoring this stuff, okay? Ignore that for just a second. Let's just look at those. Let me start by doing kind of the same thing. We'll plug in some 1s and we'll get 1 over 1, which is 1. Let's plug in 2 next. So we'd have 2 squared, which is 4, over 2 to the 5th, which is 32. That is 1/8, or 0.16, whatever it is, right? It's a little bit less than that, 1.4, whatever. Then we take 3 very quickly. Our numbers are going very large very quickly, getting kind of out of control. 3 to the 5th, we'd have 81 times 3 is 243. And so we can see that's less than 1/20th already, right? So just like above, these things seem to be going to 0. It seems like our limit is going to 0. Now, what I said though is I'm completely ignoring these back terms here. Am I allowed to do that? Well, if we're taking a really large number, which if we're going to infinity, obviously we're taking a really large number and we're squaring that, and then adding 3 times that number, what's really kind of driving that? The infinity square, the x squared, or the 3 times x? Obviously the 3 times x is making it larger, but if we said the x squared doesn't really compete with x to the 5th, well, 3x isn't going to compete with x squared. And the 5x in the denominator, same story. Even though it's just making the x to the 5th smaller, it's such a small number compared to the x to the 5th. Think about 3 to the 5th versus 3 times 5. 3 to the 5th is 243. If we subtract off 15, sure, yeah, we've lost a little bit, but it's not a whole lot in the grand scheme of things. That's only for 3. Think about when we're up to 1,000. 1,000 to the 5th is some huge number, minus 5,000. The 5,000 at that point is just basically a rounding error. And that becomes even more true as we get larger and larger numbers. So what it seems like is we are really caring about these largest powers, and that is true. But here's another idea for you. I'm always allowed to do the same thing to numerator and denominator of the fraction. So if I wanted to, I could take this thing and I could divide it by the largest exponent. So in this case, the x to the 5th. And so we'd get all these things over x to the 5th. If we think about what's going on there then, x to the 5th. X squared over x to the 5th, we could simplify that. That's 1 over x cubed. Well, we just talked about the 1 over x. That thing was running off to 0. If we have 1 over x cubed, that is going to a 0. 3x over x to the 5th, that is going to a 0. 2 over x to the 5th, that's going to a 0. We have this x to the 5th over x to the 5th. Finally, we have something that's not going to 0, that's going to a 1. This thing's going to 0, this thing's going to 0. we're left with 0 over 1, which is still equal to 0. So this can be a handy trick, especially when the exponents aren't so nice. If we have fractional exponents, or maybe if we have things like a absolute value up there, some other function that's not quite so nice as just an exponent. If we divide by that largest power, it will very quickly show us what's going to 0 and what is not, what is sticking around. Now, we've been looking at what happens when x goes to infinity, but what if I say let x go to negative infinity? Let's start with that 1 over x. Well, we're going to have actually the same exact values we did right here, except all of them now are negative. But does that change the fact that they are still going to 0? Absolutely not. If we're to look at that second example, the limit is x goes to negative infinity of the, whatever it was, x squared plus 3x minus 2 over x to the 5th, whatever else, I don't even care, right? It's just whatever it was, I think that was right. We're going to have all these values again, except they're all negative, but it's still getting smaller and smaller. It's going to 0. It's actually getting larger and larger. The absolute value of it is getting smaller and smaller. It's going to 0. So what we kind of notice is if that denominator has a bigger degree than the numerator, it seems to be going to 0. Let's take something like x goes to infinity of x. Well, clearly here, this is not going to 0. These values are getting bigger and bigger, and it is going to infinity. It's just going to grow more and more. Remember, if our limit is going to infinity, that is actually a case where the lit does not exist, right? The limit in this case we would say does not exist, but it is useful to denote the way in which limits don't exist. It could be that they're not going to exist because the left and right hand limits are different, meaning we have some sort of jump or some sort of something going on in the middle, or it could be that one of them is going to infinity. And so the fact that it's going to infinity tells us something about the function. I will always write that that limit is equal to infinity or negative infinity, but really what it's telling us is the limit doesn't exist. If you see a limit equal to infinity, that is does not exist. Now here it does matter if we're going to positive or negative, right? If I'm going to negative infinity of x, that's going to go to negative infinity. Still doesn't exist. It's just going to negative infinity. Let's say it's a little bit more complex. Let's say we have limit as x goes to infinity of x to the 5th minus 3x squared plus 2x over 3 minus x squared. Well, we can do a very similar example to what we did in the last case, which is to divide everything by that largest power. And so if we divide everything here by the x to the 5th, we can see that the only thing that's going to matter, the only thing that's not going to 0, this would be going to 0, this would be going to be this all going to 0. The only thing not going to 0 is that x to the 5th. So we'd have 1 over 0. If our denominator is growing, but the denominator is not growing quite as quickly, that thing is still going to infinity. And let's think about why that would be. Let's do kind of a little side example. Maybe I should have started with an easier case. Let's say we just had the limit as x goes to infinity of x to the 5th over x squared. Obviously it simplifies to x cubed, but let's understand why it doesn't matter that the denominator is also growing. So if we start with 1, we'd have 1 to the 5th over 1 squared, which is 1 over 1, which is 1. Then we'd have 2 to the 5th, which is 32 over 4, it's going to 8. Then we have 3 to the 5th over 3 squared, which is equal to 243 over 9, which is going to 27. So it is still growing. Even though the denominator is growing with the numerator, it's not growing at the same rate of the numerator. That thing is going to infinity. So if you happen to notice the degree at the top is bigger than the bottom, that thing will be shooting off to infinity. Now the less obvious cases, again, when we have other weird functions. But we can begin to think about what is the driving force there. So this one would be another does not exist case. Let's take the limit as x goes to infinity of 5x squared over 2x squared plus 1. Well, now the degrees of the top and the bottom are the same. They're both x squareds. And if we think about what is happening here, these things are kind of increasing at the same rate, but not quite because of their coefficients. 5 over 2 is causing those numbers to increase at slightly different rates. That 1, as we've talked about before, is just kind of a rounding error. It's just negligible once we start dealing with huge numbers. We could also divide by that largest exponent. We're going to see the 1 over x squared, that's going to 0, but the numerator is going to 5, the denominator is going to 2, and so that's our limit. That's our answer, 5 halves. So if you notice that those degrees are the same top and bottom, the degree is not causing the rate of change to be different on top and bottom, it's their coefficient, and so the coefficient is what we're going to look at. We're going to do some more examples of these in the next video when we look at asymptotes.